We're going to take a look at a quick conservation of angular momentum problem. Conservation of angular momentum works exactly the same way that conservation of linear or translational momentum worked before. The rule for using conservation of regular momentum is that there couldn't be any net external forces acting on the system. And the same thing is going to be true for angular momentum, except we have to use the angular version of force, which is torque. And so if there is no external net torque acting on our system, then the initial angular momentum of the system has got to be equal to the system's final angular momentum. And we talked about how to calculate angular momentum last time. The two main ways are angular momentum is going to be the moment of inertia times the angular velocity, or if you are dealing with an individual point mass where you are given its linear velocity, we can also do the moment of inertia for that single bit is equal to mr cross v. And also we talked about that the moment of inertia of a system is just equal to the the angular momentum of a system is just equal to the sum of the angular momentums of the parts. Whether you think of them as little l's or big L's, when you add them all together, you're going to get the total angular momentum of our system. And so for this problem, let's assume we have a person who is sitting in like an office chair or some sort of chair that can spin, and they are holding a couple of bowling balls out. And they start rotating. And then as they're rotating, they're going to bring the bowling balls in closer to their body. So at the end, it's going to look more like this. And so the question is, what's going to happen? And if we think about what's happening in terms of the moment of inertia, we know that the moment of inertia will be smaller the closer the mass is to the axis of rotation. In this case, we've kept the mass the same, but we've brought it closer to the middle. And so at the end, they should have a smaller moment of inertia than they did at the beginning. Well, if their angular momentum at the beginning has to be equal to their angular momentum at the end, if the moment of inertia goes down, the angular speed has to go up. So we would expect them to now be spinning around somewhat significantly faster than they were before. And so we're going to try to figure out exactly how fast that is. To solve this problem, the assumptions we are going to make is that the mass of our person is 100 kilograms. And the person is roughly, we're going to treat them as a solid cylinder with a radius of 0.25 meters. For the bowling balls, we're going to assume that the mass of the bowling balls is 6 kilograms each. And we're going to treat them as point masses. Which obviously they aren't, but the alternative is that we have to treat them as solid spheres and then use the parallel axis theorem. Since they're relatively far out from the axis of rotation, though, it's not a horrible approximation to just pretend they're point masses, just like pretending that a human body is roughly cylindrical. And we will assume that the bowling balls in the beginning started at a radius of 0.9 meters, and at the end The bowling balls have a radius of 0.3 meters. And so the things I would like you to find. I would like you to find the moment of inertia of the system, both at the beginning and the end. And I have used my space poorly here. So that's the first thing I need you to find. So just the moment of inertia. And then if our initial angular velocity here is, let's say, 0.5 radians per second, what is the final angular velocity? So at the end, if they were spinning at 0.5 radians per second, how fast are they spinning at the end? So I'll give you a moment to pause the video and then try this problem on your own, and then we'll go over it together. Okay. So the first thing I asked you to do was figure out the moment of inertia of the system at the beginning and the end. And so the moment of inertia of the system we know is just equal to the sum of the moments of inertia of the parts, which in this case is going to be the moment of inertia of the cylinder plus the moment of inertia of one of the bowling balls plus the moment of inertia of the other bowling ball. I guess I've switched back and forth between geometry here, but this is the person. Is our cylinder, and then the bowling balls are our points. So that is going to be a cylinder is 1/2 the mass of the cylinder times the radius of the cylinder squared. And then for a point mass, it's just going to be the mass of the point times the radius the point is at squared, and there are 2 of them. Which, of course, we can just combine this and get 1/2 the mass of the cylinder times the radius of the cylinder squared plus 2 times the mass of the point mass times the radius of the point mass squared. And so for our initial conditions, our initial moment of inertia is going to be 1/2. Our cylinder was our person. That was 100 kilograms. The radius of the person we said was 0.25 meters. The mass of the bowling ball was 6. And the radius that the bowling ball started at initially was 0.9. And so if we plug that all in, we're going to start with a moment of inertia of 12.845. This is kilograms. This is meters squared, so kilogram meters squared. Okay, so that's our initial moment of inertia. Our final moment of inertia for our system, same thing, except we're going to use the ending radius that the bowling balls end at, so we'll use a 0.3 here. So it's going to be 1/2 times 100 times 0.25 squared plus 2 times 6 times 0.3 squared. And that's going to come out to be 4.205 kilogram meters squared. Is our final moment of inertia. And then the last thing we wanted to do is figure out what the final angular velocity is. And so to do that, we know that the moment of inertia, or the angular momentum at the beginning, has to equal the angular momentum at the end, which means that the initial moment of inertia times the initial angular velocity has to be equal to the final moment of inertia times the final angular velocity. So that's going to be, so you could either just put it all together. The final angular velocity is going to be the initial moment of inertia times the initial angular velocity divided by the final moment of inertia. And certainly you can just plug everything in. I'll do this in a couple of steps so we can sort of see along the way some numbers that are going on that some of you might have calculated. So plugging everything in here, we're going to have 12.845 times 0.5 divided by 4.205, which is going to become 6.42-ish divided by 4.205. And this is the initial angular momentum of the system. So this quantity that we calculated up here, that's the angular momentum, which, remember, since it stays the beginning at the end, that just is the angular momentum. So if you calculated that, it's 6.42. If you never found it along the way, that's fine. I didn't ask you to explicitly find it. But if we take the angular momentum and divide it by the final moment of inertia, that should give us the final angular velocity. And so what we wind up getting as our answer is about 1.53 radians per second, which is consistent with our prediction. We expected them to speed up when they brought the bowling balls in closer to their body.